Welcome. In this video, I discuss orthogonal bases, positive definite case. Before going to the general case, I discuss the example of R2. For R2, I consider three bases as beta 1, beta 2, and beta 3. In beta 1, we have two vectors 2, 0, 2, 2. In beta 2, we have 2, 0, 0, 2. And in beta 3, we have 1, 0, 0, 1. If we plot the vectors of these bases, we notice that in beta 2, we have an additional feature. That is, the vectors of beta 2 are perpendicular to each other. In beta 3, there is one more additional feature, which is that the vectors are perpendicular to each other, and one additional feature is that each of the vector is a unit vector. So, if the vectors of a basis are perpendicular, then we call such bases to be orthogonal bases. And if in addition to orthogonality, the length of each of its vector is 1, that is, each of its vector is a unit vector, then we call it an orthonormal basis. So let V be a vector space with a positive definite scalar product. If we consider a basis of this vector space with vectors v1 up to vn, then this basis is said to be an orthogonal basis if the elements of the basis are mutually perpendicular. That is, the scalar product of vi with vj is 0 for I different from j. And if in addition, the elements of this basis satisfy this property that the norm of each of its vector is 1 for each I, then we say that this basis set is an orthonormal basis of the vector space. For example, if we consider Rn, then the unit vectors 1, 0, 0, 0, 1, 0, and the last one is 0, 0, 1. This is an orthonormal basis of Rn. Now the problem is that if we have a basis of a vector space, how can we shift that basis into an orthogonal basis of that vector space? So we discuss the following theorem. This theorem states that if V is a finite dimensional vector space with a positive definite scalar product, if you take a subspace W of this vector space and there is a basis of vectors W1, Wm of W, which is an orthogonal basis, then there exist elements Wm plus 1 up to Wn such that the set W1 up to Wn is an orthogonal basis of V. In other words, an orthogonal basis of a subspace of a finite dimensional vector space can be extended to an orthogonal basis of the larger vector space. The method of the proof is very important. This is known as the Gram-Schmidt process. And how do we prove the result? Let us see. So, since the set W1 up to Wm is a basis of this subspace of V, W, by a previous theorem we know that this basis of W can be extended to a basis of V. And hence, we can find elements Vm plus 1 up to Vn such that the set W1, W2, Wm, Vm plus 1 up to Vn is a basis of V. The issue is that all these elements up to Wm are orthogonal. But Vm plus 1 may or may not be orthogonal to these elements. Hence, we use a theorem that we studied in our previous lecture, wherein we studied that if V1 up to Vn are non-zero elements of a vector space and they are mutually perpendicular, then if Ci is the component of V along Vi, then V minus C1 V1 minus Cn Vn is perpendicular to V1 up to Vn. And hence, we use this idea in proving this theorem. How do we use it? Let us see. So we consider a subspace of V which is generated by W1, W2, Wm and Vm plus 1. And we find an orthogonal basis of this subspace. Now, since Vm plus 1 is not perpendicular to W1, W2 up to Wm, hence we use the concept that we discussed here. What do we do? That we take Vm plus 1, here we took a vector V, then we subtracted the projection of V1 up to Vn from V, and the new vector obtained is perpendicular to V1 up to Vn. Hence, here we take Vm plus 1 and we subtract the projection of W1, W2 up to Wm from Vm plus 1, and hence the new vector obtained will be perpendicular to W1, W2 and Wm. So for that, let C1 be the component of Vm plus 1 along W1. C2 is the component of Vm plus 1 along W2. It is given by this thing. And Cn is the component of Vm plus 1 along W1 given by this thing. And hence, we construct a new vector Wm plus 1 as Vm plus 1 minus C1W1 minus C2W2 minus Cnwn. And now Wm plus 1 is perpendicular to W1 up to Wm. And hence we construct the new vector Wm plus 1 as this one, Vm plus 1 minus C1W1 minus C2W2 minus Cnwn. And hence, by our previous discussion, this Wm plus 1 is perpendicular to W1, W2 up to Wn. And additionally, this Wm plus 1 cannot be 0. If we assume it to be 0, then from here, if this is 0, then Vm plus 1 can be written as C1W1 plus C2W2 plus Cnwn. And hence, Vm plus 1 is dependent on W1, W2 up to Wn, and which contradicts our supposition wherein we took that Wm plus 1 is the span of these vectors. Hence, Wm plus 1 cannot be 0. Now, since Wm plus 1 is perpendicular to W1, W2 up to Wn, hence W1, W2, Wm and Wm plus 1 is an orthogonal set. And hence, by induction, we can proceed that the space Wm plus s generated by the vectors W1, W2, Wm, Vm plus 1 up to Vm plus s has an orthogonal basis as W1, W2 up to Wm plus s, with s is equal to 1 up to n minus m, and hence it proves our theorem. And we have a corollary of the previous theorem that any finite dimensional vector space with a positive definite scalar product, and assume that the vector space is a non-trivial vector space, then V has an orthogonal basis. And the process that we discussed earlier can be summarized as follows. So let V be a vector space with an arbitrary base V1 up to Vn as this one. And the problem is to orthogonalize this basis. So how do we orthogonalize this basis? We consider V1 dash to be V1. We take V1 dash to be exactly this first vector. Then what do? V2 dash is equal to V2 minus the projection of V2 on V1 dash. And we know that this is now perpendicular to V1 dash. Similarly, we construct V3 dash to be equal to V3 minus the projection of V3 on V2 dash minus the projection of V3 on V1 dash. And now we know that this V3 dash is perpendicular to both V2 dash and V1 dash. And lastly, Vn dash is equal to Vn minus the projection of Vn on Vn minus 1 dash minus and so on minus the projection of Vn on V1 dash. And we know that this vector is now perpendicular to Vn minus 1 dash, Vn minus 2 dash up to V1 dash, and hence the new set of vectors which forms a basis of this vector space V is an orthogonal basis of V. And if in addition we want to normalize this basis, then what do? We divide each vector by its norm. V2 dash by its norm, and the last one is Vn dash divided by its norm. And hence this set form an orthonormal basis of V. Now we discuss an example. The problem is to find an orthogonal and hence orthonormal basis for the vector space generated by these three vectors. So assume we call these vectors as A, B and C vectors. Then the first thing is to compute A dash, and we know by our previous discussion that A dash is equal to A. The next step is to compute B dash, and B dash would be equal to B minus the projection of B on A given by this one. And if we compute B dot A, we know that this is B, this is A. So if compute B dot A, it is 1 minus 2 plus 0 plus 0. Hence this is minus 1. And if we compute A dot A scalar product with A, hence this is 1 plus 1 plus 1, which produces 3. Hence B dash is equal to 1 minus 2 0 0 minus 1 over 3, which is plus 1 over 3, and A is 1 1 0 1, and hence it produces the vector 4 by 3 minus 5 by 3 0 and 1 by 3. This is B dash. How do we compute C dash? C dash is equal to C minus the projection of C on A given by this one minus the projection of C on B dash, which is given by C dot B dash divided by B dash dot B dash B dash. And if we simplify this, the answer that we receive is minus 4 by 7, minus 2 by 7, minus 1 and 6 by 7. And hence the new set of bases given as 1 1 0 1, 4 by 3, minus 5 by 3, 0 1 by 3 and minus 4 by 7, minus 2 by 7, minus 1, 6 by 7 is an orthogonal basis of the vector space. And if we want to find the orthonormal basis, we divide each of these vectors by their magnitudes to have an orthonormal basis of this vector space. Thank you.